the class goes a lot smoother, makes it a lot more interesting if you guys speak up. So if I ask a question, please jump in. You don't have to raise your hand or anything. And please feel free to interrupt me at any time if you have a question. So the first place we want to start off, we talked about some of that basic calculation and basic properties of numbers a little bit last time, just to kind of get you to familiar with how things interact. And it actually is very important in algebra to have that count and that name. Today, we're going to start out by looking at sets of numbers. And we're going to go through them rather quickly, just because we've all seen them before. The two most basic sets that we usually encounter first in our life are the counting numbers and the whole numbers. Both of these include the positive numbers 1, 2, 3, 4, 5. The difference is, of course, the whole numbers include 0. Counting numbers, if there's nothing there, there's nothing to count, so you don't need to include 0 in that. And those are what we typically encounter first. Going up from there, we encounter the integers. Integers include the whole numbers, but they also include negatives. But it's good to note that there are still, even though we have positive and negatives, there are still no fractions and no decimals. In a pre-algebra class, we would spend a lot of time working with those integers, those negative numbers. We'll spend a little bit of time reviewing that in here, partly because working with negatives is vital for being able to work with our algebraic numbers. But hopefully you guys all have a little bit of a background with that coming in. Beyond integers, our next set is something called rational numbers. Rational numbers are actually a rather large set. They include anything that can be expressed as a fraction. In other words, anything of the form A over B. Now, there are very few real numbers that cannot be expressed as fractions. All of our repeating decimals can be expressed as fractions, even though we can't express them really as a decimal very well. They can always be broken down into a fraction. So the question is, what is not rational? Which is usually referred to as the irrational numbers. Well, probably the most common ones that you've seen are the famous pi from working with circles. That's 3.14159, blah, 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 blah. It goes on forever. Never repeats in a predictable pattern, never terminates. That's irrational. That cannot be expressed as a fraction. The natural number, e, is another one that cannot be expressed as a fraction. Along with those, any number that does not have a, excuse me, losing my voice on the first full day of classes here. Any number that's not a perfect square, if we take the square root of it, 2 isn't a perfect square, so the square root of 2 is an irrational number. The square root of 3 is the irrational number. That will go on forever without repeating. As if we write it as a decimal, it will go on forever without repeating or without terminating. Now the square root of 4, 4 is a perfect square, so that's just 2. That's rational. But the square root of 5 is irrational. Square root of 6, and so on. Other roots are irrational if they're not perfect. Like the cubed root of 5 would be irrational. And again, other indices of our roots. Both those rational and irrational numbers come together to make up what we call the real numbers. Real numbers are just that. They are numbers that can express physical amounts, physical values. So values that we can experience in nature, natural calculations and stuff like that. Well, what is outside of the real numbers? There's something called imaginary numbers. Now, some people might think we got enough trouble with real numbers. Why are we making stuff up? Well, the imaginary numbers really not as complex as they seem. The imaginary numbers are based off of the square root of -1. If you try to punch the square root of -1 into your calculator, it's going to give you an error. It's going to say it's not possible. And in real, your calculator only is capable of working with real numbers. In real numbers, the square root of -1 is not possible. But we made up the imaginary number system to work with those negative square roots. So back into the real numbers. A lot of what we do, we didn't get to the number line last week, but a lot of what we do works with a number line. For example, if we're asked to round 3,472 to the nearest hundred. We talked about those place values last week and how they're so important in defining our operations with numbers, the addition, subtraction, multiplication, division. Place values also become very important in rounding. Of course, what digit in this number is in the hundreds place? 4. There we go. This is the ones, tens, hundreds, and thousands, 1,000s. So that 4 is in the hundreds place. Well, when we're asked to round to the nearest hundred, what it's literally asking us to do is to look at a number line and only consider the markings that are at the 100 intervals. And if we put 3,472 on here, which would be somewhere in here, physically, which of those hundreds is it closest to? 3,500, perfect. It's physically closest to the 3,500. So when we round to the nearest hundred, that's how we round it. So of course, we don't want to draw out number lines every time we round, so we learn shortcuts. As we mentioned on Wednesday, most of what we've learned in math is a shortcut to make a real process quicker and easier to manage. So when we round 3,472 to the nearest hundred, we were taught to first find the hundreds place, which is the 4. Then what do we do? Okay, we look at the number to the right. Well, what we're getting here, the information we're getting, when we find that this is a 4, that's telling us on the number line we are between 3,400 and 3,500. When we look to that number at the right, well, that's telling us it's a 7. If we think of the space between 3,400 and 3,500 as being divided up, you've got 1, 2, 3, 4. 5 is in the middle. 6, 7, 8, 9. 7 being in that next digit is telling us that we are most definitely closest to the next one up rather than the one down. So that's telling us that we round that up to 3,500. So yeah, we're taught that, that digit, whether it's, bigger than 5, we round up, smaller than 5, we round down. Again, that's a shortcut. That's physically telling us which spot it's closest to on that number line. What if it were a 5? What if instead of 3,472, what if that were 3,452? What would that round to the nearest hundred? When that next digit is a 5, what have we been told to do? Round up. If you asked why, you were probably given, well, we've just accepted that that's what we do. It's a convention, right? Somewhat true, but not really. That's not just 50, that's 52. So 52 is somewhere in here. It really is closer to the next one up. It's past halfway. The only way that that's exactly halfway in between, if that's 3,450. Now it is exactly in the middle. And in that case, yes, we just have accepted that next digit's a 5, we're going to round up. If any of you plan on going into any sort of engineering or mechanical design field, there are processes out there where they round when that next digit's a 5 and it's followed by zeros, where they will round part of them up and part of them down. The reasoning for that is so there isn't error buildup, rounding buildup. Mostly it deals with decimals, really small decimals. If you have 4.3875 and 2.8425, and we're rounding everything to the nearest thousandth, I should say, the nearest thousandth. Both of those are going to round up. And what we get when we add those, if we're adding those together, is we're going to get a measurement that's a full thousandth larger than it needs to be, which is okay if we're just adding 2 numbers, but if we have 5 or 6 numbers, now we're a few thousandths larger than what we should be. And that can be an issue in precise engineering applications. So in engineering, and I'm not going to go over it here because I don't want to confuse you. For this class, we always round the 5s up if that's the next digit. But there are processes out there in engineering where if that next digit's a 5 and there's nothing after it but zeros, sometimes they round it up and sometimes they round it down. If it's something you're really curious about, let me know and I'll show you sometime outside of the full class, but I don't want to confuse everybody with showing you that process right now. So one of the other things that number line is used for is to express numbers. If we have 0 here, obviously the positive numbers go to the right, negative numbers go to the left. We can express, let's say, the value 7. A lot of us are used to just putting a dot on the number line at 7, and that represents the value, but it's not a very useful representation. What we often, a more useful representation than just a dot is something called a vector. That's a very fancy word for a really simple concept. All a vector is an arrow that starts at 0 and goes to that number. So the vector for 7 starts at 0 and it goes to 7. That's the vector. So then the vector for -6 starts at 0, goes to -6. Oops, get back there. So then when we deal with vectors, there's something called magnitude. Magnitude is just the length of a vector. Magnitude does not depend on direction. Length does not depend on direction. The symbol that's used looks like this. And that symbol is referred to as the absolute value symbol. And what it's asking us to do is to find the magnitude of the vector. Well, we drew the vector for -6 up here. It's the one in green. How long is that vector? Don't be shy. 6 units, exactly. The absolute value of -6 is 6, because that vector is 6 units long. Another definition of absolute value is simply distance from 0. So if we're not using vectors, if we're just using a dot, we just put a dot at -6. Well, again, the distance of that from 0 is just 6 units. So it works out the same either way. Definition varies depending on what representation we're using for those numbers. I like to use vectors because when we talk about operations with integers, vectors describe how we combine those numbers. If I have 5 plus 3, most of us have just memorized that 5 plus 3 equals 8, of course. But if we didn't have that memorized, we could calculate it using vectors. Vector for 5 looks like that. The vector for 3 looks like that. Adding means literally just combining vectors. So to add 5 plus 3, we just take the vectors and we put them together. When I put those vectors together, they give me a total length of 8. So 5 plus 3 equals 8, because that's what I get when I combine the vectors. When we talk about integers, we're going to use that same representation to help us simplify those calculations. So to continue with some of our review of pre-algebra for today, one of the other concepts we have to be familiar with is exponents. Exponents, we look at things like this. How would we pronounce that? 8 cubed, or what's another way of pronouncing it? 8 to the third power. If we were to calculate it, how would we calculate it? There we go. 8 times 8 times 8. It's 3 8s multiplied together. It's repeated multiplication. Of course, that multiplies to be 512. Is there anybody that's not sure how to use the power key on their calculator? Okay, if you do have any questions that come up with it, let me know. So that exponent is nothing more than repeated multiplication. Now, when we talk about integers, there's going to be an issue that comes up there. -5 squared and -5 squared. Theoretically, those appear to be the same, but to your calculator, they are different. To your calculator, this one is saying -5 times -5, -5 squared, which is 25. This one is saying 5 squared and then make it negative. So 5 squared is 25. It's making it -25. Just a word of warning, when you're dealing with those negative numbers, make sure you know what you mean when you enter the calculator. Because if you truly are squaring the negative number, it has to be in parentheses. So these exponents have two parts to them. That 8 to the third power, or 8 cubed, if you will, has a base. That base is the number that is being acted upon. In this case, it's the 8. And then the other part is the power, which is telling us what action is being done to it. Power of 3 means the 8 is being multiplied by itself. 3 of them multiplied together. It's going to be very important when we look at our rules of exponents, because x to the third power times x to the fifth power operates very differently than x to the third power times y to the fifth power, because they have different bases. So we haven't done anything with fractions yet, so it's time to put something in there. We're going to assume coming in that you guys are good with your basic operations with fractions. If you have any questions there, let me know. I did put some review videos out on Blackboard for you too that have fractions in them if you need to brush up on them a little bit. 2/5 to the third power. 2/5 times 2/5 times 2/5. When we multiply fractions, we combine counts, or we combine numerators. 2 times 2 times 2. Well, that's just 2 to the third power, or 8. And then we combine the counts, or combine the names, I should say, combine the denominators. 5 times 5 times 5, well, that's just 5 to the third, or 125. 2/5 to the third power is 8 over 125. So when we have a fraction raised to a power like that, we can separate it. So there's the numerator of that power over the denominator of that power. 3/4 to the power of 5 can be broken down. 3 to the power of 5 over 4 to the power of 5. Now, I don't necessarily expect you guys to know your powers up to the fifth power, but 3 to the fifth power is 243. 4 to the fifth power is 1,024. 24, not 25. So 3/4 to the fifth power is 243 over 1,024. Can that be reduced? Good question. Can 3/4 be reduced? No, it can't. If this original fraction can't be reduced, the power can't be reduced. Remember, when we're reducing a fraction, you can think of it as factoring and then canceling common factors. For example, 12/30. If you factor 12, 12 is 2 times 2 times 3. You guys remember how to do prime factoring? Factor tree. 12 might break into 2 times 6. 2 is prime. 6 breaks into 2 times 3. Those are prime. So 12 is 2 times 2 times 3. Look familiar? 30 factors into 2 times 3 times 5. If I'm reducing that fraction, I can cancel out a 2. I can cancel out a 3 in the numerator and denominator. I'm left with 2/5. That would be my reduced fraction. Well, here, remember 243 came from 3 to the 5th power. 1024 came from 4 to the 5th power. Technically 4 is 2 times 2. All I have is 3's on top and all I have is 2's on bottom. There's nothing that cancels out there. So if it can't be reduced before we take it to a power, it cannot be reduced after. Bless you. Before I do a power of a decimal, just off to the side here, I'm going to do a quick review. We mentioned it a little bit last Wednesday. If I have 0.05 times 0.7, when I multiply that, 7 times 5 is 35. Where does my decimal point have to go? Yeah, we count. Perfect. We count 1, 2, 3 decimal places in the problem. So in our answer, we go 1, 2, 3. So we got to put a 0 in there. Decimal places in our answer. With that in mind, when we square a decimal, 0.02 squared is really 0.02 times 0.02. How many decimal places does this answer have to have? 4. So 2 times 2 is 4. That's 0.0004. If I have 0.05 to the 6th power, how many decimal places is that going to have? There we go. If I write them all out, there's 6 of them, and each has 2 decimal places. My answer has to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. Now, 5 to the power of 6 is 15,625. 0.05 to the power of 6 is 0.0000001565, because we have to have those decimal places. Everybody's used to when you square something or take something to a power, it gets bigger. That's only because those numbers are larger than 1. Of course, 1 to any power. What's 1 to the power of 274? 1. 1 never changes. I can take it to whatever power I want to. It's still going to be 1. So things that are bigger than 1 get larger as we take their powers. Things that are smaller than 1, as we saw up here, can get quite a bit smaller as we take them to a power. One of the simpler, more basic concepts in pre-algebra and algebra And probably one of the most powerful, most used, is our order of operations. Order of operations, a lot of people think of as being a set of rules, a set of steps for solving problems, for combining numbers. It's not really true. It's really levels of priority. And when we're faced with a problem, if a number has two different operations that it can be used with, we have to do the one that has the highest priority first. Those levels of priority, the highest priority is something called enclosing symbols. Many people refer to this simply as parentheses, but it's actually, there's several other types of enclosing symbols out there. There's different types of brackets and parentheses, but there are other enclosing symbols that we'll run into as we do some examples. The next level of priority is those exponents. Now, we've explored the powers of exponents here first. Exponents, however, also include roots. Our third level of priority is multiplication. As we mentioned last Wednesday, multiplication and division are really the same operation. One's just a forward movement and division's moving backwards in the process. So multiplication and division are happening at the same time. They're on the same level. They're the same operation. And finally, our lowest priority is addition. And as we mentioned last week, subtraction is part of addition. So even a relatively simple problem like this can get confusing rather quickly if we don't use our order of operations. So if we look at our order of operations and our levels of priority, are there any enclosing symbols? No. Any exponents? No. Multiplication or division? There are a couple of them. When there's more than one on the same level of priority, then we work left to right. So going left to right, first we have the 7 times 8, which is 56, right? And now technically, we should do that one operation where we take two numbers, combine them to make one number, and replace them. The rest of the problem should stay the same. Now we're still multiplication and division, moving left to right. We see the 3 times 5, which is 15. So once again, we remove those two numbers and replace them with that single number of 15. And now all that's left to do is 56 minus 15, which is 41. Perfect. Now, many of you probably would have taken shortcuts on this, and that's fine as long as you know you're safe doing them. Since the 7 times 8 and the 3 times 5 are separated, you could do 7 times 8 is 56, 3 times 5 is 15, and not have to rewrite the problem in between. That's okay. But if you're ever unsure, step by step is the safest way to go. So obviously that one is relatively simple. Let's step it up just a bit. Something like this. This has a little bit of everything in it. We have enclosing symbols, the parentheses. So that means we are looking at that blue box there, what's inside the parentheses first. We're not looking at any of the rest of the problem. Now, inside there, order of operations still applies. Are there any other enclosing symbols? No. Exponents are next. Are there any of those? 4 squared, which of course is 16. So replace the 4 squared with 16. Still inside the parentheses, any other exponents? No. Multiplication and division? Yeah, so what are we going to do first? 3 times 8. There's more than one of them, so we're going to go left to right. So 3 times 8 makes 24. So replace that with 24. Still inside the parentheses, what has to happen next? Now we're doing multiplication and division yet, going left to right. The next one is the 24 divided by 6, which is 4. Good. I know it's tedious to rewrite the problem every time like I'm doing here, but I've found through the years that most of the mistakes people make on these are not trying to avoid writing down the whole problem, and they end up, making a mistake because they missed something. We're still inside the parentheses. All we have left is addition and subtraction. So what do we do next? Perfect. 16 minus 4. They're all both on the same level. So we go left to right. 16 minus 4 makes 12. Perfect. Now there's only one thing left to do inside the parentheses. 12 plus 5 makes 17. Now that the parentheses is down to a single number, we don't need the parentheses anymore. We can get rid of the enclosing symbol. Once there's only a single number inside of it, we can get rid of it. Now, technically, I should rewrite this first with the parentheses there, first step, and now take them out. When I take those parentheses out, I have to be careful. Is there anything being done to that parentheses that I have to make sure is still there once I take them out? Perfect. There is a 2 in front of the parentheses with no operation there. This actually happens in all sorts of enclosing symbols. Whenever there's a number outside of an enclosing symbol with no operation, that is implied to be multiplication. So when we take out the parentheses, we have to make sure we keep that multiplication there. So we have to put in that symbol. Now, order of operations still applies. We're done inside those parentheses. We go back. Are there any other enclosing symbols? Say no. No. Any other exponents? No. Multiplication, division? Yes. 2 times 17 is 34. Perfect. Next. 5 plus 34 is 39. And then minus 3 is 36. Most of the mistakes I see in a problem like this on a quiz or a test come before you even start. I will see people take 5 plus 2 and get 7 and run that through the whole rest of the problem. What is wrong with that? There you go. If I look at just that 2, yeah, there's addition here. It's added to the 5, but there's multiplication on the other side. Which has a higher level of priority? That multiplication, right? So when I'm dealing with that 2, I cannot add it. I can't do this addition until I have done this multiplication. It has a higher priority. When we look at a problem like this is still order of operations. We see this line across here. What does that line mean? It means division, but there's more to it. It is also an enclosing symbol. It's called a fraction bar, and it does mean to divide. But before we divide, because it separates the top from the bottom, before we divide, we have to do everything on top first. Then we have to do everything on bottom. Then we can divide. So it is another form of enclosing symbol. So I'm going to take the top here and I'm going to rewrite it so I can work with it. So I've got room. What am I going to do first on top there? 5 squared makes what? 25. Perfect. What's next? Seven times 8 makes? 56. Very good. And then? (56 minus 25 makes) 31. And finally, add 2. 31 plus 2 is 33. So the top of that fraction is 33. Any questions there? So now I have to do the bottom. What do I have to do first on bottom down here? Seven squared is 7 to the power 2 is 49. And then 76 divided by 2 makes 38. I'll help you with that one. And then 48 minus 38 is 11. So the bottom is 11. So then all we have to do is divide. We've reduced everything on top to a single number, everything on bottom to a single number. So we can divide. 33 divided by 11 is 3. Perfect. Another form of enclosing symbol that we'll run into might look like this. Yes, this is a square root symbol. It's actually called a radical. It's used for other things other than just square roots. But it's also an enclosing symbol. There is more than just a single number inside of it. So we've got to start out by doing what is inside of that radical. So inside there, order of operations still applies. What has to happen first? 9 times 3, which makes 27. Then what? Add the 1. So that becomes 28. Now that we've reduced what's inside that parentheses to a single number, just like inside that radical to a single number, just like in parentheses, when we're down to a single number inside, we can get rid of that enclosing symbol. The difference is in parentheses, we take it out and that's it. Some other enclosing symbols, when we take out the enclosing symbol, there's an operation we have to do. Here, we actually have to take the square root of 28. Now, that's going to be an irrational number. So I shut my calculator off. Let me turn that back on. So we'll have to calculate the square root of 28. And in a problem like this, we should specify what we're rounding to. So let's say that I'm going to tell you round to the nearest thousandth. So we do the square root of 28. We have 5.2915. What do we round that to? 5.292. So we've removed the square root symbol and we've done the square root of 28. What else do we have to remember to do here as we remove that square root symbol? Yeah, just like when there's a number outside of parentheses, that 3 in front of the radical is multiplied. Now what? Three times 5.292 is 15.876. And then add the 7. Perfect. 22.876. Now, obviously, I don't expect you guys to do these calculations without a calculator. As we mentioned last week, do some estimating first. You know that 5 squared is 25, so you know the square root of 28 is going to be just a little bit bigger than 5. That makes sense. 3 times 5 is 15, so 3 times 5.292 is going to be a little bit bigger than 15. So use those estimates in your head, so as you're punching in the calculator, if there's a mistake, you catch it. Many calculators, depending on what style you have, that square root key is the second function to the squared key. So if you screw it up, that can give you some really weird answers if the second key doesn't register. The calculators are here, and I acknowledge that they're going to get used, but make sure you have that idea, that estimate in your head before you start punching in the numbers. Well, we've mentioned some other forms of some other operations that come into play in our order of operations. One of them is that absolute value again. We might have 5 minus 2 times the absolute value of 11 minus 3 times 6 plus 1. So again, we have our absolute value symbols right here. Those are an enclosing symbol. Just like parentheses or radical, we have to do what's inside there first. What has to get done first in there? 3 times 6 is 18. Very good. Now there's only one thing left to do inside the parentheses. 11 minus 18, which is -7. Now we're down to a single number inside that enclosing symbol, inside our absolute value. So again, we can get rid of that enclosing symbol. Just like with the radical, though, we have to do something when we remove it. We remove the absolute value symbols. What's left there? It's a +7. Remember, the length of that vector is 7 units. Or you think of it as -7 is 7 spaces from 0. The other thing we have to remember to do there is to put in that multiplication. Now, of course, we keep going with our order of operations. What's next? 2 times 7 is 14, yep. And then? Five minus 14 is? Add and subtract left to right. That's going to be a -9, right? -9 plus 1? -8. Good. A little bit of a side note. We have been taught a process to circumvent order of operations a little bit. It's called distributing. And we were told that distributing is a way to get around our order of operations. We might have something like this. Well, typically, we would want to do 5 plus 2, which is 7, right? And then do 3 times 7, which is 21. But distributing allows us to do this. What's 3 times 5? 15 plus what's 3 times 6? Or 3 times 2 is 6. I gave that one away. And 15 plus 6 is 21. We get the same result. The problem I have with defining distributing like that is, why on earth would you want to go through this much work when you could just do 5 plus 2 is 7 and multiply by 3? This is making it a lot more work. Distributing only really applies when what's in here cannot be combined. Like when we get into algebra, you might have 5 times 2x minus 7. Now distributing makes sense because the 2x and the -7 cannot be combined. They're not like terms. The other reason I bring up distributing right now is this here. There's a mistaken notion out there that you can distribute through an absolute value. And that is absolutely not true. If I were doing this with my order of operations, I'd do the 5 minus 11 first, which is -6. What is the absolute value of -6? 6. So I remove the absolute value symbols. That becomes a +6. And of course, I put in that multiplication. What is 3 or -3 times 6? -18. If I try to distribute that, I would be -3 times -5 is -15. -3 times -11 is +33. -15 plus 33 is 18. The absolute value of 18 is not -18. So it doesn't work. So I bring that up. Hopefully nobody looks at that and thinks that it's okay to to distribute through an absolute value symbol. It is not. It causes all sorts of mistakes in our calculations. Distribution should only be done in this case where what's in that enclosing symbol cannot be combined. And even then, it should never be done in an absolute value. Now, there are all sorts of other places where enclosing symbols come into play when we least expect them. Something like this. It doesn't look like we have enclosing symbols here, but we do. In our exponents, there's more than one thing to do there. So we must do that piece first. There's no symbol there at all, but that really is an enclosing symbol, that power of the exponent. So we have to do what's in that power first. Of course, we do the 3 times 2, which is 6. Then what? 11 minus 6, which is 5. Now we have to do 2 to the power of 5, which is 32. Then what? Oops, put my 3 back in there. Then what do we have to do? 5 times 32 is 160, and then plus 4 gives us 164. Very good. Any questions there? We can run into issues like this, where we're asked, usually the command we're given is to evaluate, and we're told for C equals 8, A equals 5, M equals 3, P equals 4, and D equals 9. So there's really 2 things we're being asked to do here. First, we're being asked to substitute these values into this expression. In other words, complete the expression. So 5C becomes what? 5 times 8. Yes, that's technically 5 times C. So we'll put 8 in for C. It's 5 times 8. Minus 2A becomes 2 times 5, and then minus 3. Perfect. I'm not going to combine any of them yet. I want to substitute first, then we'll start our order of operations. On bottom, P squared, of course, becomes 4 squared minus 9. What do we do next? Well, it's a fraction bar. It's an enclosing symbol. We have to do everything on top first. So I'm going to write it over here so I have room to work on it. What do I have to do first there? 2 times 5 makes 10. And then 10 minus 3 is 7. Now I can get rid of those parentheses, can't I? I don't need them in there anymore. What's next? 5 times 8 is 40. Minus 7 is 33. Very good. What do we have to do first on the bottom here? 4 squared is 16. 16 minus 9, 7. So we got 7. So now we divide out. 33 divided by 7. Oh, what is that? Like 4.71428571443 approximately. Or 4 5/7. Any questions? Okay. So we have about 10 minutes left. I want to just touch on what we're going to start with tomorrow. And that is what I think is, in the long run, the most difficult task in math. And that is translating between words and algebraic formulas. Now, what we're going to look at today is relatively simple, but it gets more and more difficult as you look at word problems and pulling the information out of a situation to create those phrases and formulas and symbols and equations. Let's start out with something simple like 7 more than a number. Well, first let's talk about that number, that mysterious number. Well, of course, we're going to represent that number with a variable, right? And it could be X. You're absolutely right. It could be Y, it could be N, it could be A, it could be the pound sign if we wanted it to be. A variable is any symbol that is used in place of a number. Now, typically we stick to letters just to make it simpler. When you get into trigonometry, they use Greek letters, alpha, beta, theta, all of those. But it's a symbol that's replacing that number. Now, your homework is in my math lab. The algorithm for my math lab is relatively simple. What I mean by that is it doesn't think like a person does. 7 more than a number means 7 is being added to something. And let's just say we put X in for the number. We call it X plus 7. Well, somebody else might write that is N plus 7. Is there any difference between those? No, they mean exactly the same thing. We just chose a different symbol, a different letter to use as our variable. Well, in my math lab, the computer algorithm can't tell that those are the same. So we have to be careful in my math lab. It will tell you use N for the variable or for the missing number. So make sure you're careful to look at that and see, oh, it wants me to put N in there, so I'll put N in there. So 7 more than a number meant addition. There are all sorts of other phrases that mean addition. Can anybody think of any of them other phrases that would also be written as N plus 7 or X plus 7? I'll give you the easy one. A number plus 7. Any others? Greater than, 7 greater than a number? That works. Yeah, 7 greater than a number means 7 has been added to it. You got to be careful. The word is would change that. If you said 7 is greater than a number, that makes it that greater than symbol. This thing, right? Greater than, less than. Any others? Throw out the fancy word, the sum of a number and 7. What's the word sum mean? Yeah, sum means total or the result of an addition problem. If I tell you a number reduced by 3, I tell you to use p as our variable. How would I write that? Very good, p minus 3. Any other phrases you can think of that would also be expressed as p minus 3? There we go, that's a good one. The difference of a number and 3. Any others? Yeah, a number minus 3. Any others? To go along with yours from addition, instead of greater than, less than, 3 less than a number. A very important note I want to make here, side note. Up here, would it make a difference if I wrote 7 plus n? Is that any different from n plus 7? No, it's the exact same thing. Down here, would it make a difference if I wrote 3 minus p? Yes, that makes a difference. I cannot do that. When it comes to math, our basic operations are commutative. Remember, we mentioned on Wednesday that addition and multiplication are our basic operations. They're commutative. The inverse operations, which are the subtraction and the division, are not commutative. So when we add or multiply, we can switch the order. When we subtract or divide, we cannot. We have a couple minutes left, but that is a good place to cut it off. Tomorrow we'll keep going with that translating words into symbols. There is a My Math Lab. Your first homework assignment is out there. It's going to be homework 1A. Again, it is listed in My Math Lab as being due tomorrow, Tuesday, at 11:59 p.m. And I do highly recommend that you have it done by then. That gives you a chance to work on it tonight, ask questions in class tomorrow if there's any questions that come up, and then it gives you plenty of time to finish it up then tomorrow night if you need to. The absolute deadline for that homework, again, is on the 28th, which would be next Monday. Every Monday we wrap up the previous week. So anything from the previous week is past its deadline on that Monday, put it that way. But again, I highly recommend you have it done by tomorrow night just to help you pace. Otherwise, you end up with like 120 homework problems to do for Monday because especially early on in the semester, some of these homeworks, a lot of them are 30 to 40 problems each. Any questions on the day? Okay, well, you guys have a great day and we will see you all tomorrow. It does get more exciting, I promise. Off. You bet. Have a good one.